Hello everyone, welcome to this online course on material science. This is lecture 22 in the module 1 on magnetism. Today we will see how the paramagnetism can be modeled in terms of quantum mechanical consideration. And the reference for this lecture is the standard textbook on magnetism from Stephen Blundell. The title is Magnetism in Condensed Matter from Oxford University Press. So if you recall, in the last few lectures I have given you all the angular momentums of an electron so that you understand how this paramagnetism can be modeled, right? And I want to start by saying that we will discuss the paramagnetism in an atom, right? And for the kind of atom that we want to consider here is partially filled, right? That's one important thing to remember, because if you recall that if the atom has a field shell, then the diamagnetic contribution usually dominates, right? So to study the paramagnetism, we need to consider an atom with partially filled electronic shell, right? That's like the kind of model we should have in our mind, right? So partially filled electronic shell, and in that shell we will have a number of electrons, right? And we know that electron has two types of angular momentum. One is the orbital angular momentum and the spin angular momentum. So if you recall that our total angular momentum, let me denote it by AM. So the total angular momentum is denoted by J, right? The vector operator J, and it's nothing but the sum of the orbital angular momentum and the spin angular momentum, right? And if you recall also that total angular momentum squared, this operator commutes with any three components of the angular momentum, which is Jx, Jy, and Jz. But in our discussion we will consider this commutation, and if you recall, this is 0, right? It means J square and Jz has common set of eigen vectors, and we can operate on the same state by these two vectors, right? So by these two operators. So, and if you recall, the state for this total angular momentum, we need two quantum numbers, right? J and mj. So we have discussed these things in details in the previous lectures. And also recall that for the operator, when acts on some state with j mj quantum number, right, this will produce nothing but j plus 1 h bar square and then the state itself, right? And also the jz component operator, when acts on a state with j and mj level, this will bring out the quantum number mj. So it should be mj times h bar times jm, right? So these are the things we have discussed in last few lectures. And also, if you remember, this mj quantum number runs in the range minus j to plus j in the steps of unity, right? So if somebody asks you how many mj allowed values you have in this range, as this is running in the steps of unity, there should be 2isj plus one number of different mj values starting from minus j to plus j, right? And now the question is to ask is that when you want to understand magnetism, you should ask yourself, let's say, what is the magnetic dipole moment corresponding to this j operator, right? So we have some electron, and electron has total angular momentum, and we are asking what is the magnetic moment operator of the electron due to this angular momentum. So you remember, right, that we have some g factor, which is usually the lambda g factor, and we know the expression explicitly in terms of quantum number L, S, and J, and that's the lambda G vector. And we have the Bohr magneton divided by the h bar times the total angular momentum, right? That's the definition of magnetic momentum operator. And also one point to remember is that this operator, the J, is a vector operator, so it must have three components in three-dimensional space, right? So you can write it as Jx times, that's an operator, times some unit vector along x, plus you can write Jy, that's an operator, times some unit vector along y. Let me denote the unit vector by Jy, and also the Jz times maybe some unit vector along z-axis, which is kz, right? So that's the vector expression. And now, for paramagnetic discussion, you always put the atom inside a magnetic field, right? And the type of magnetic field we use in our problem, so we will apply some magnetic field, and the magnetic field is a constant magnetic field, and it points in the direction which is usually the z direction, right, which is the canonical direction. So our applied magnetic field, let's say it's some constant value which doesn't depend on space or time, just a fixed number times the kz, right, unit vector along z-axis. So that's your moment, that's your magnetic field, and we are trying to understand how the magnetic moment will behave in the influence of this magnetic field. So the next question we should ask is that, okay, inside this magnetic field, what should be the energy of that electron? But we know this sort of expression because I have discussed this in previous lectures, that the energy of a magnetic moment which is denoted by this mu operator in the presence of the magnetic field is nothing but minus mu times the magnetic field, right? And that's a vector, and inside that vector what we have is G, right? So we have G mu b by h, right? And then we have J times, so that's like our magnetic moment operator, and then we dot it with the magnetic field, right? Now, if you remember that in our expression, magnetic field points along z direction, right? So if you dot this vector with this one, the only jz will survive because this vector doesn't have any component along x or y, right? So for this, you will have G mu b by h, and sorry, so I'm using yes. Oh, so now the question is G mu b by h, and then only the component along the z-axis times the magnetic field, right? So that's the dot product of J times Bz, and that's an operator, right? The energy operator for the magnetic moment, and that's how you express the operator. Now the question is, how do you find out the expectation value of this operator, right? Because that's your energy and you want that value. How do you find out the expectation value? And the thing is that you have to know that what state you are talking about, right? So you have the operator, but you have to sandwich the operator between a Bryce state and a Ket state, right? As the operator is Jz, you know the quantum number should be J and Mj, right? And here the same, J, Mj. So now you can put the operator inside this expectation value. So let me write it JMJ, then we have minus G mu B by H times JZ operator times the magnetic field, then JMJ, right? So these are just some numbers. The only thing is the operator. We will keep the operator inside the expectation value and bring everything out, because B also a number which is the magnetic field strength, right? So let's bring everything out from this expression. So we have G, we have mu B, we have H and B outside. Inside we have the bra JMJ, then the operator JZ, and then JMJ, right? And you know what's the action of this operator on this state, when operator on this ket vector. So let me write it there. So we have J mu B by H, magnetic field. Here we have JMJ, and this is nothing but MJ times the H of JMJ, right? And this is just a number, so you can bring out this number from there. So we have minus G mu B B H bar, and then MGH, and the inner product between bra JMJ and ket JMJ. So from the notion of the orthonormality, we know this is 1, and so the expectation value of energy is just this one, right? That's 1. So you can write, and you can cancel this H bar with this H bar. So you have G mu B B times MJ. So that's the expectation value of energy, which is the value of energy itself, right? So that's the expectation value, which is nothing but the energy itself, right? So that's the expression for the energy, and we will use this energy expression to find out the magnetization under the influence of the magnetic field, right? And the next lecture I will show you how you can perform the averaging on this state and then try to calculate the susceptibility for paramagnetic material. And for this lecture, I think that's about it, and thanks for listening.